So here we are. That's the main image in English of my university. Just to give it a name, it's Hochschule Karlsruhe, University of Applied Science. We're sitting in Karlsruhe, that's in the southwest of Germany, quite famous for its investigation in artificial intelligence and man-machine communication, and a lot of other fields. So I really invite you to visit the website, especially the students, to see what occasion we have also for foreigners from Mexico, for instance, to stay with us in for a externalship or something like that. So let's come to the presentation itself after this short advertisement. Okay, that's our new logo. We are really proud of it. That's valid since yesterday. So yesterday we changed our logo, so probably not everything will run as we want. Here's my email address if you like have further questions, and that's the already mentioned and already shown website. So what's about the talk? The talk is going about motion time prediction in human-computer interaction. So actually, the question is, how can we model performance of humans when they are interacting, like I'm interacting now with the hardware with my screen using a mouse device with marking some text, for instance. But what is the performance here? How fast can we do such a thing as a human with a mouse or as a touch display or using a pen, whatever device we like to use? In the second part, I'd like to show some links to information theory. So actually we're transforming information, and the question is there any link? And actually there is a link, and I'd like to show that link during my talk. And finally, I'd like to show some machine learning approaches we are doing currently in our labs just to get better prediction. So performance prediction, of course, is a nice field for being investigated by artificial intelligence as well. It's currently the hype, so we have to follow that one also, of course. Yeah, so the central question is, how do users perform in non-verbal, so using mouse or something like that interaction? I'd just like to show you an example, or actually that's the client we are using to do our experiments, and that's here. So here are some variables we can influence during an experiment. So I can switch, sorry, that's in German, but anyhow, I can switch on or off if I want to have circles and so on. So some test variables can be set here. I give my name and what's happening with that experiment. And then I start the experiment. And then targets show up, and I have to move with the mouse to the appropriate target. And as soon as I touch the target, the next target will show up. Yeah. And simply the question is, can we model that? Can we work with that in mathematical manner? And actually, very long time ago, for the students especially, very, very long time, some brilliant researcher in United States have established research into that direction. Remember, there was no computer mouse, there was no no touch device. He did that with electronic equipment, like in this picture. So he did experiments with testing persons. They had a pen and 2 copper plates. And then the bell was rung, and the people had to move the pen from one copper plate to the other. And they took the time, how long did it take to get from one copper plate to the other. And that was the experiment in 1954. Yeah, and there were 2 variables they investigated: the distance of the target from the starting position and the width of the target. So he took several sizes of widths, and so he had different experiments. So a bit more abstract, we have the distance from the starting point to the target, and we have the width of the target. That's of interest in the formula for the prediction of the movement times. So, and he found his famous index of difficulty formula. And it goes like that. He takes the logarithm on base 2, and he's got the two variables. The distance is in the counter, so the farther an object is away, the more difficult is it to click or to touch on it. And in the denominator, he has got the width of the object. So the smaller an object becomes, the more unlikely, the more difficult it is to do the movement job. And he established, interesting, as early in 1954, the unit bits following Shannon's research that was done some years earlier at those times. Okay, and what he did then, he did a lot of experiments with different widths and with different distances A, and obtained different index of difficulties here on the x-axis. And he obtained, of course, different times for the task he tested with his users. And the result is drawn in, that's the really the initial paper's drawing, and you can find that is in his initial publication. And you can see quite well that the behavior of the experiments is more or less linear. And so therefore he calculated the regression line and obtains two parameters. The intercept, that's A, here in that drawing, and he obtains the slope of the regression line. That's the second parameter he received from his experiments. With those two experiments, now he and we, anybody can predict future movement times. So if I want to know how long does it take to get from here to there, I just calculate the ID of that movement, the index of difficulty of that movement task, multiply it by the slope, add the reaction, the activation time, and obtain a prediction of the movement time. So that's an important point to just stop a second and ask for questions. Are there any now? We are now at the end of the first chapter. Any questions here? Okay.
Please continue, Doctor.
Okay, thank you. Okay, so anyhow, so this actually does the job. We can predict movement also on computer screen, but we have some problems with that. The first and biggest problem is it's metric. So the dimensions for A and W, the width of the object needs to be found in meters. And that's really a complicated thing for computer scientists, because we have so many different screen sizes, from a small smartphone up to a 80-inch scaled TV set that nowadays is available for some few €100. So if we want to take Old-Fitts law, we have to take metrics and use a ruler and get how big is such button, and that really is a bit cumbersome, not easy to use. More important, we can, in that formula, we can get negative movement times. As soon as W gets really huge and the distance gets really small, then we can get negative movement times. And that, of course, is useless, because there's no such thing like negative time. And more important for augmented reality or for virtual reality, there we not only want to control some point on the screen, but we want to control things in 3D space. And here we have no such thing like simply width and distance. We need rotation angles. And here's the question, how can we incorporate that task not only to control the distance, but also to control the orientation? How can we model that one? And finally, that was elaborated quite well by Heiko Treves in his paper, Only One Fits Formula, Please, in CHI conference in 2010, with actually link to Shannon. Where does the unit bit come from? That still remains hazy. And I try now to give some answers to those questions. Yeah, so in order to do though, I'd like to dive a bit into the basics of information theory first. Yeah, so what I want to work with is a term self-information, or some say information content. People from coding theory, from compression algorithms know that well. We're talking there from symbols. So we have n symbols, x1 to xn. So let's say letters in an alphabet, A, B, C up to Z, or we have digits we transmit on a wire cable, 0, 1, or we have 3, -1, 0, 1, or we have 10, 0, 1, 2, up to 9. We have different symbol sets, and these symbols are stand for x1 to xn. Yeah, and unfortunately, those symbols in real life do not occur on equal base. So in German, for instance, the letter A is a quite common, E is a quite common letter, or in English as well, whereas the letter Y or Q or Z are letters that are really uncommon. So these symbols have different probabilities. And from that fact, we can define this self-information or the information content of a single symbol we know as being the, again, logarithm dualis, also so logarithm base 2, from the symbol of interest, its probability. Again, the unit is bit. Here I've got a drawing of the self-information on y-axis and the probability on x-axis. So we can see here, for instance, that when we have a symbol that has a probability of 1, so it's the only symbol we see, and it's always that simple, so it's symbol, so it's always present, then we have a probability of 1. And that gives in the formula logarithm dualis from 1, returns and self-information of 0, meaning if you know something for sure, we do not gain any information. That's useless. On the other hand, the closer, though the smaller the probability gets, the higher the self-information gets. Here we have an asymptotic behavior towards the y-axis, meaning we have a saying in press industry, only bad news are good news, because only when something is really, really bad, a train accident or something like that, this is quite uncommon. So the probability is very low. And on the other hand, the self-information of that event is very, very high. And that is can be all be drawn from that simple curve. Yeah. So here's another example just to work a bit with that self-information term, tossing a fair coin. So we have two possibilities. We can throw a coin and obtain either a head or a tail. So in that case, the experiment has two symbols, head and tail. And because we have a fair coin, we have for both the same probability, always in half. And if you want to know, okay, I have seen a head after showing a coin, then I know the information content by that formula. So I take the logarithm dualis minus often half, and that gives 1 bit. So two cases, so quite simple to see that we have 1 bit as information gain when we know the result of that tossing of a fair coin. Okay, and now we can make a linkage between that self-information term I just introduced and the trying to pre-calculate movement times, and it goes like that. So what we actually need is a probability of a window object like a button, for instance. So what's the probability if I click arbitrarily on that screen anywhere? And if I count all these non-hits and all hits and divide by the numbers of hits that were successful, I will find sooner or later that the probability of hitting that button is simply the number of pixels on the button divided by all pixels of the screen. That's a probability that we hit onto that very button. Having that on hand, we can calculate the self-information And that gives us, like in the formula of for self-information. And then we do just the same as Fitz did. We just do linear regression, obtain the coefficients A and B, and can then predict the movement time by that formula as I marked here down. Yeah. So the trick is to determine probabilities of interaction objects, in that case simply counting pixels and dividing by all pixel, and we can proceed to predict our movement times. Okay, so here's an example how to use that formalism. So I want to know how long does it take to click on the button C1. I have given the extensions in Y and X directions. I know the width of the test app screen, and then I can simply calculate the probability by multiplying out the buttons pixels and the screens pixels, obtain the possibility. There, from that I calculate the self-information, and having that on hand, I can calculate the movement time from any point to that C1 button. Okay, what are now the advantages? I have no longer to deal with meters or inches or something like that. I only count pixels and done. No need to have a ruler or something on the screen to measure how big a button is. It fits to the rest of the information theory quite well. Some examples. That formula here says the smaller a button is, the longer it takes to click on it. Or that formula is quite easy. Here we say as soon as a button is as big as the whole screen, then we have a probability of 1. Then we only need the activation time. It's independent from the slope. It's just as soon as you can see the button and try to click anywhere on, and decide to click anywhere on the screen, you get a hit. So you only need the activation time for that case. On the other hand, the other case is here. When a button is not on the screen at all, then you have 0 pixels on the screen, and then the movement times will be infinitely long. So if it's not on the button, it takes infinitely long to click on it. Also a good interpretation on the other side of the axis of the self-information axis. And that's been shown in the next slides. It can be easily extended to higher dimensional systems, and quite simple. Of course, I can not only calculate my button like that, like in a rectangle, but I can also count the pixels of a circle, of a tree, of a menu, of whatever I want to predict how long does it take to click on it. Okay, first for higher dimensional systems. Here I've got a picture of experiments we did at our university. Here's a testing person. Here's a 3D monitor that is used by having a stereo glasses, the testing person, and his 2 hands virtually operate such a coat hanger. So virtually he operates this white coat hanger and tries to move that white coat hanger onto the position of the green coat hanger, and to manipulate the orientation of the coat hanger such that the coat hanger, the green and the white coat hanger, are at the same space, at the same place, and have the same orientation with a certain accuracy that was given by the experiment. And then as soon as he hits the coat hanger with the right orientation, the next coat hanger shows up where he has to move next. Yeah. And the formula to calculate the probability that he has got the right orientation and the right place in 3D space is here. That's the accuracy of the volume, so that he's on the right place. It's simply the sphere formula here. And this is the probability of being the right yaw angle, and that's the probability to be at the right roll angle. So 2 angle probabilities multiplied by the accuracy probability gives a probability. From that we calculate the self-information, and those dots here are the experiments results we did. We averaged the results for an interval of 1 unit, so of 1 bit of self-information. And then the red diamonds show quite well for the averages that we have really quite well a linear behavior. And we must see that's 60 interaction. That's not so easy as going around with the mouse. On the screen, we see here that it takes a while. So on average, such a coat hanger movement takes 4 to 5 seconds. But anyhow, we can predict it using that formalism, using the probability, calculating the self-information, and using linear regression like the black line indicates. Okay, for 2D, we investigate several possibilities to calculate the probability of a click event. The first one I already have shown. We take the pixels of the target and divide by the pixels of the application. That can be done a bit more accurately by not dividing by all pixels, but by all pixels of the bounding box. So the interaction starts here at point x1, and the user moves to the target T2, and we take the target space divided by the bounding box space and obtain such our self-information for a bounding box. Or even more elaborate, we take not the bounding box, but the bounding polygon that's spanned by the target, and here by a triangle that is spanned by the starting point x2 and the target itself. Okay, and that approach using the polygon can be extended to case order Markov models. So going back in the past several steps by simply multiplying not only one, but several polygons with an attenuation factor of 1/8. That's a heuristic that was found to be useful in the experiment. We need some more work to ensure that this is a real good value, but anyhow, it works quite well. So we do not take only into account the actual movement, but also the movements in the past. So doing that, we punish zigzag designs where the user has to go from here to there, from here to there, and we support designs that are on a straight line, because then the volume gets smaller and the prediction in the denominator gets small. The number of pixels in the denominator gets smaller, and such we get a better interaction prediction. Yeah. So we did that for about 20,000 clicks experiments, and as one could expect, talking on correlations, the simplest method is the worst, and the most elaborate, the most complicated method is getting the best correlation. So that's no wonder. The better the model, the better the prediction will be. We know that also from machine learning, that the better the model, the better the results get. What was interesting and not awaited by us is that the really simplest model, so just counting pixel, was for touch devices like smartphones, tablets, and so on, competitive, at least to Fitz's law and to the ISO norm of motion prediction. Why is this the case? Actually, at the beginning, we were puzzled and didn't understand it. Why do we get so good results for such a simple model? And then we looked what the people did when they interacted with the buttons. And they started interacting with the buttons and their finger. They did like that. They took their tipping finger and tipped from one target to the next one. But sooner or later, they used 1, 2 fingers, 3 fingers. Some used 5 fingers. Some people even used all fingers of the hand. and the one finger that was closest to the next target was taken to hit onto the target. And then the model of a straight line going from here to there, of course, is wrong. And the simple model that simply counts pixels gets better and better. And that one is really simple to calculate. That's a simple sum of rule that everybody can use to predict motion times, because it's stateless. And that's a nice finding, that for touch devices, but meanwhile, as the majority of all devices on the world, most people use smartphones and tablets, no longer mice to interact. We can use such a simple interaction technique. Prediction. So what are we currently doing in our research? Yeah, so we had results, but we didn't know what is the best result we can get from the data we have collected with the experiment. And so we decided to dive into machine learning algorithm. And questions were, are there any variables we can influence as a designer? So rules like all your buttons must be in a straight line, or you should not move from right to left. It's better to move from left to right with the user, and such things more. That's were the questions. And here we found, okay, really important is the history of movement. And that is what we are currently working on more to get more and better results. So we began to use simple tree algorithms like random forest or XGBoost regressor. And that are algorithms that you can get from the shelf, no need to preparate. That can be used really quickly. And we put into those models more data, for instance, the age and the gender of the testing persons. And even so we entered more data, we didn't really receive better results. If you talk on mean absolute error, that's not really significant. Here we have a 3, that's 6 units, 6 milliseconds difference. That's not really a lot. A bit better, but also not too good, is the XGBoost regressor. Actually, we were not really satisfied. Even so, we spent more data. We did receive not really better results if you compare to the baseline algorithm of Fitts law. We wanted to take tree algorithms in order to get explainable models we can understand and can we work with. And so we gave up that approach and got to neural networks. Here we have a SHAP plot where we can see the influences of the different variables. And here we can see the distance is the most important thing. Second is the user age. Though elder people are worse in interaction with mice and touch, and so on and so on. What we have seen, and that was the interesting part, that the direction of the second last, the third last, and fourth last interaction also play an important role in the prediction. And so we investigated further. The question is, how many steps back from this last interaction, second last, and so on, how many steps, what is n? What is the n that still has influence on the prediction power of our prediction algorithm? If we know that, we can see, okay, you have to take care when designing to look not only on the current interaction step, but also back to the, let's say 1, 2, 3, 4, 5, 6 last interaction steps. And so we received a number we had not expected. The mean absolute error went down the more we took past variables into our model. And at, let's say, 7 or 8, it is saturated and gets no better. That means we don't know yet for sure, we have to look back 5 or 6 steps in order to have an optimal or near to optimal prediction. Yeah, and here the numbers really got better. Initially we dealt Fitts law with 224 milliseconds mean absolute error. The neural network with only 1 with 0 history information is lots better, but we can have it, the prediction power, the prediction error, by using lots of direction variables into the past, into our model. Yeah. So, and another, that brought us to another mind switch. Up to then, we were searching for design rules. So do this and you get such number of milliseconds faster. The idea we follow now or have had recently is, why should we do the design if there's something like neural network already available that knows how fast something will be in the future? And that is what we are currently doing, having not accomplished yet, is having a generative adversarial network in order to have a given lousy, not so good design of a graphical user interface, have that and use the already present predictor, let the discriminator give critique until we have a better design that has a summative movement time that is better than the initial given graphical user interfaces. That is what we are currently working on. The main showstopper currently is to get the right hardware, because it's so hard to get fast hardware. That's currently what I'm doing. Yeah, that's for that one. I'm finished. I'd like to answer your questions, and I have written here preguntas, si quieren en español, pero un poco lento, por favor, si me preguntan algo en español. Muchas gracias por haberme y estoy abierto a sus preguntas.
Bueno, acaba de terminar su conferencia el doctor Ulrich. Pregunto a la audiencia si tiene alguna cuestión que le quiera hacer al doctor Ulrich. Si no, yo sí quiero hacerle una pregunta, doctor. In your opinion, what are the main problems left in the human-computer interaction?
The main problem currently, that's a difficult question. The diversity of interaction paradigms, I think. We have so many things on market, then they have very few standardization. Every year a new way of interacting comes around. So we had, voice user interfaces was 3 years ago. We had augmented reality was a hype some years ago. We had, even more years ago, virtual reality being hyped. We had glasses being hyped again by Apple, probably. And so every 2 years there's a new hype, and actually none up to now, except for touch devices, really did catch on. The really big progress was now 13 years ago with Apple coming out with the iPhone, and from that point on, there was a lot of progress in science, but not as real progress on market. That really did not happen. A lot of things, and leaving behind a huge number of different possibilities to interact, and we need, in my opinion, more standardization, making it easier to learn how to interact. We have so many possibilities. So if you swap, for instance, from Mac OS to Windows to Linux, it's always a lot of work. And it's even harder if I think about 3D interaction. We have there near to no standardization, at least which axis is going from you out into the world. Is it the Z or the Y axis? That's not standardized. You find frameworks where it's the Z axis, and you find other frameworks where it's the Y axis. That's really bad, because you have to learn for both how to rotate things with using dial knobs or something like that. So the higher the dimension, the less the standardization. That's my opinion. Yeah, and that makes the thing so hard to use sometimes.
Muchas gracias, doctor. Hay tiempo todavía para otra pregunta. Esta es una pregunta del ingeniero Miguel Ángel Ricciotti desde Montreal, Canadá. La pregunta es, what is the difference in accuracy for the machine learning compared with the deep learning?
Yeah, I go back some slides probably for that one.
Please.
Oops. 1 second, I have to move the videos away. So machine learning is here. So that's what we can do with Fitts law, no machine learning. Baseline algorithm having to do nothing with machine learning, keras and all that stuff. And here we use random forest, that's machine learning algorithm. We have near to no, let's say 217 milliseconds mean absolute error. And on the other hand, we have, if we take the same data, we have 181, that's error, that's 182, that's a lot better. Yeah, so getting smaller errors, that's asymptotic. It's not linear. It's really hard to get the last 10%. It's not linear. And therefore, this one using a lot of directions as further input variables of the last interaction that halves both the baseline algorithm and the machine learning algorithms like tree algorithms, XGBoost, for instance. Is this okay? I forgot, by the way, something. I put into this chat the slides. They can be downloaded. Yeah. Where is it? Here. So if you want to see once again the slides, you can receive them there. Is this? Can you see that? In the chat? Yes. Okay. Is that question okay to the person from Canada?
Sí, doctor. Pues creo que ha abundado usted bastante en el tema y pues no me queda más que agradecer su participación y y pues que quede abierta la invitación para que usted continúe dándonos algunas otras conferencias en el futuro. Muchísimas gracias, doctor Ulrich Broekl.
Muchísimas gracias a usted. Con mucho gusto, es un honor, era un honor de participar en este evento. Muchas gracias.
Bueno, hasta luego.
Hasta luego.